Alright, we are in section 11.3, talking about the integral test and estimates of sums. So, what we've been looking at so far when it comes to series is a little bit abnormal, because typically we are not really able to find a simple formula for the partial sums S sub n. So we need to come up with different ways of determining convergence or divergence without actually having to find the sum, because oftentimes that's just not practical or not even possible. So the first test that we're going to look at starts tying in the concept of improper integrals from back in chapter 7. So if you need to go back and review that a little bit, then you should go and do that, but we'll also be doing some examples with it here in a bit. So the first series I want to look at is the series of the form 1 over n squared, okay, from 1 to infinity. So that's just the sum of all the reciprocal squares. So 1 over 1 squared plus 1 over 2 squared, etc., etc. Okay, now the graph to the right, whoops. So this graph on the right over here, the red graph, that is the graph of 1 over x squared. Okay, so this is the corresponding function that goes along with that sequence or that series. So the rectangles underneath that curve represent an approximation to the area under the curve. So if we're looking at what these areas are, that's going to be width of 1 for all of these, and then the height is determined by the function for each of these rectangles, right? So this is going to have an area, well, the first one would have an area of 1 times 1 over 1 squared. The second one has an area of 1 over 2 squared, right, because it's the output at 2, then the output at 3, output at 4, etc. So 1 over 3 squared plus 1 over 4 squared, etc. Those are the areas of the rectangles. But that is just the same thing as the series we're looking at, right? From 1 to infinity of 1 over n squared. Right? So it turns out that finding the value of the integral is actually going to give us a value we can use to help determine the series. Okay? So if we exclude the first rectangle, okay, because our series only starts at 1, right? So it starts at n equals 1. So ignore the first rectangle, and the rest of the areas give an area that is less than the area under the curve for x greater than or equal to 1. Right? The area of the rectangles from here onward is going to be less than the area under the curve, okay, because it's an underestimate. Okay? And so this area under the curve is given to us by this improper integral. So we actually saw this one back in 7.8, and this improper integral is convergent, so we can deal with that. Find its value. Its value is 1. So that means that the partial sums are less than, don't forget we excluded the first rectangle at first. So we have the first rectangle, we have the first rectangle plus the area under the rest of the curve. So that's 1 plus 1. $1 million question for the day, so that's 2. So that means the partial sums are less than 2. So thus the partial sums are bounded. Okay, so they're bounded below and above. We also know that they are increasing. Okay. And we know they're increasing because these are all positive values, right? So the partial sum, remember, it just takes, the first term, the first term, that's S1, right? S2 is the first term plus the second term. S3 is the first plus the second plus the third, right? So because all these values are positive, it's increasing. Okay, even though the function f of x is decreasing. That's not what we're looking at. So the partial sums converge, therefore the series converges, and the sum of the series is less than 2. Okay, so we don't know that it's exactly 2. We're saying that it's less than 2, okay, because that area is 2, and it must be less than that. Okay, so we can also look at a series like 1 over the square root of n, with n going from 1 to infinity. So the areas of these rectangles with base width 1 and height determined by the function 1 over root x give us, right, this series of terms, right, heading off towards 1 over an infinitely large number. This total area is greater than the area under the curve for x greater than or equal to 1. So you can see here in our rectangles, right, we have an over approximation here, so we're going over the curve with all of these. So this is given to us by the improper integral. Okay, so that gives us the area under the curve, and we know that our value, right, our sum, is going to be larger than that, okay, because we're above the curve. So from section 7.8, this integral is divergent, so this area under here is already divergent. Okay, we showed that back in 7.8. So that means that the area under the curve is infinite, which means the sum of the series must also be infinite. Right? Because if this portion down here is infinitely large, then adding more onto it is certainly still going to be infinitely large. Thus, we say the series is divergent. Okay. So these two examples are kind of the basis of what we call the integral test. This is how we're going to be able to determine convergence and divergence using improper integrals. So suppose that f is continuous, positive, and a decreasing function on the interval from 1 to infinity, and let a sub n equal f of n. Then the series from 1 to infinity of a sub n is convergent if and only if the improper integral from 1 to infinity is convergent. Okay, so this gives us two statements here. So if the improper integral is convergent, then the series is convergent. And if the improper integral is divergent, then the series is divergent as well. Okay, now we do have to have these conditions, right? Continuous, positive, and decreasing on this interval. But if we have those conditions, then just finding the improper integral is sufficient to determine convergence or divergence of the series. Okay, so a couple of notes here to take notice of. The series and integral do not have to start at n equals 1. So we could be starting at n equals 2, 3, 4, 5, it doesn't matter, because in the long run, right, starting at, if the value was infinitely large before, right, when we started, so if we had, a function that looked like this, so if the area starting at 1 is infinitely large, certainly the area at 2 is also going to be infinitely large. It doesn't matter that we took off this one little piece, right? We can start even at 10, and this would still be infinitely large because we just took off a finite piece of it. Okay, so it doesn't have to start at 1, but that's typically where we do begin. And then the second note here, the function f does not have to be strictly decreasing, but rather the long-run behavior of the function must be decreasing. So the function can increase. It doesn't have to be always going down. You could have, like even oscillating functions where the function kind of does a little, bouncing as it's heading towards the asymptote, horizontal asymptote, or the x-axis. But as long as overall, in the long run, you get the value of the function is decreasing. Okay, so getting smaller, closer to 0. All right. Let's look at an example. So test the series 1 over n squared plus 1 for convergence or divergence. All right, so let's make a note over here. So f of x, so let's write the corresponding function. So 1 over x squared plus 1. So we can talk about the required pieces here. So this function on the interval from 1 to infinity is continuous, right? Because x is being squared, it will always be positive. And as x gets larger, the denominator gets bigger, which means the whole thing is getting smaller, which means that it is decreasing. On the interval, so it's closed at 1, and then open at infinity. Oops. There we go. Okay. So our function f of x is continuous, positive, and decreasing on the interval 1 to infinity. So we can say, thus, we can use the integral test. Okay. And these are the type of conditions that it might not seem that important to check them, but it is, because if you don't have these conditions met, we can't use the test, and the test will give you faulty information. So just have to make sure that you're verifying that when you're doing this. So because we can use the integral test now, let's look at the integral instead of the series. So we have the integral from 1 to infinity of 1 over x squared plus 1 dx. Okay, so using an improper integral, we need to write it as a limit of a finite integral. So limit as t approaches infinity of the integral from 1 to t of 1 over x squared plus 1 dx. Okay. Now we go ahead and take the antiderivative. So antiderivative of 1 over x squared plus 1, that's a special one, but that one is the inverse tangent. So we have limit as t approaches infinity of inverse tangent of x evaluated from 1 to t. So this is the limit as t approaches infinity of inverse tangent of t minus inverse tangent of 1. Inverse tangent of 1, that's going to be pi over 4. So we're left with limit as t approaches infinity of inverse tangent of t minus pi over 4. Okay, now as t goes to infinity, you might need to look at the graph of inverse tangent to really identify what's happening on this graph, but as t gets larger and larger and larger, the inverse tangent function is actually approaching pi over 2. Okay, so this one is actually just going to be pi over 2 minus pi over 4, which is pi over 4. Okay, so what this tells us is the improper integral from 1 to infinity of 1 over x squared plus 1 dx is convergent. Okay. And the integral test tells us that because these conditions up here were satisfied, if the improper integral is convergent, the series must also be convergent. So we can say, thus, the series 1 over n squared plus 1 is convergent. Alright, so we do get convergence for this one by that integral test. Okay. Now I do want to make a note here, so we can just put this right here. So we got the value of the integral was pi over 4. An important thing to note, the integral test does not tell us what the value of the sum is. Okay? It doesn't tell us what the series adds up to. So the integral test does not tell us the sum. So generally, the value of the integral and the sum of the series are not the same. Okay, so that's an important thing to take note of here. Okay, so generally speaking, the value of the improper integral and the sum of the series are not the same. So this problem is not telling us that the series converges to pi over 4. It's just it's telling us that the integral goes to pi over 4. But the integral and the series are not the same thing. Okay, so they give us different pieces of information. We're just saying that if the integral converges, then the series also converges at the same time. Okay, it doesn't mean they go to the same thing. Okay, so let's look at the next one here. So for what values of p is the series 1 over n to the p convergent? Okay, so let's look at a couple cases here. So let's start off, so if p, let's start with less than 0. If p is less than 0, then the limit as n approaches infinity of 1 over n to the p. So if p is negative, that means you have the n value getting larger and larger. P is a negative power in the denominator, right? So 1 over, and if this is a negative number, that's going to move it up to the top, right, like that. And if n is getting larger and larger, this is going to become infinitely large. So if p is less than 0, then that limit is infinity. And if p equals 0, the limit as n approaches infinity of 1 over n to the p, well, n can be as large as we want, and if it's still raised to the 0 power, then anything to the 0 power is 1. Okay, so that's going to be 1. Now, in both these cases, it didn't matter whether the limit was infinitely large or not. What really mattered, was whether the limit went to 0 or not. So since the limit did not approach 0, the series diverges. The series diverges by the test for divergence. Okay, so since the limit does not approach 0, then the series diverges. Okay, so if we have that p is less than or equal to 0, we have divergence. So now let's look at what happens when p is greater than 0. So if p is greater than 0, then f of x, our corresponding function of real numbers, 1 over x to the p, is continuous, positive, and decreasing on the interval from 1 to infinity. Okay, so that's going to allow us to use the integral test on this series for p-values greater than 0. And then, just to note, back in Chapter 7, we found the improper integral from 1 to infinity of 1 over x to the p dx converges if p is greater than 1 and diverges if p is less than or equal to 1. Okay, so we can see that the integral is convergent for p greater than 1 and diverges if it's less than or equal to 1. So we can use that same value for our integral test. So by the integral test, the series one over n to the p, if I can write the letter p here, 1 over n to the p. So this series converges if p is greater than 1 and diverges if p is between 0 and -1. So let me fix this here. So, and diverges if p is between 0 and 1. Okay, also inclusive of 1. Alright, so by the integral test, we have the series converges if p is greater than 1, and diverges if p is between 0 and 1, inclusive of 1. Okay, and if we have the case where p equals 1, so just as a side note, so when p equals 1, we already talked about this series. This is the harmonic series. Right, that was just 1 over n, right, or 1 over n to the first, if you want to look at it that way. That was the harmonic series that we dealt with. So that one is familiar to us. So this type of series, so the series 1 over n to the p, because we have such a clear picture of when it's convergent and when it's divergent, this one actually gets used a lot. This has a special name, so this is called the p series. Okay, and the p series, so 1 over n to the p, is convergent if p is greater than 1, and divergent if p is less than or equal to 1. Okay. So, we can do just a quick example here. So determine convergence or divergence for the following series. So we have 1 over n cubed. So in this case, this one is p series, so recognize that pattern here. So this is p series with p equal to 3, which is certainly greater than 1, which means that it's convergent. Okay, and that's really all there is to it. Okay, as long as it matches this p series format, then we can use this argument for it. Okay, and then this one is also p series, so it has that same layout. With, in this case, p is 1/3, so it can be fractional, right? With the root, which is certainly less than 1, which means that this one is divergent. Okay, and the p-series, kind of from a more logical standpoint, the p-series is basically telling us if the power is high enough in the denominator, it's going to shrink faster and become really small really fast. So it's going to converge a lot faster, whereas with this, if p is really small, then that's actually going to grow a lot more slowly and gradually, which means there's a lot more area under the curve, which gives it a better chance of being divergent. So there we have just a couple of quick examples dealing with the convergence or divergence using a p-series. Okay. So next up, let's look at a little more complicated of an example here. So determine whether the series ln of n over n converges or diverges. So in order to determine if we can use the integral test here, we need to look at the corresponding function of real numbers. So that's going to be f of x equals ln of x over x. So for this one, we know that this is positive, right, for x greater than 1, and continuous, right? The only discontinuities would come when x is 0 or below. So and continuous for x greater than 1. Okay. However, when we're talking about whether the function is decreasing or not, that's not directly obvious in this case, so we need to actually check. Let's go ahead and verify that it is in fact decreasing. So, but it's not obvious if it's decreasing. So let's check. And how do we determine if a function is increasing or decreasing? Well, by taking a derivative. So throwing it back to Calc 1 a little bit here. So let's get the derivative of this function. That's going to require use of the quotient rule. So that's going to be, right, low d high minus high d low. So that is x times 1 over x minus high d low, ln of x times 1 over low squared. So that's just 1 minus ln x over x squared. Okay, so what does this tell us? Well, this gives us, so f prime of x is less than 0, so that slope, that derivative, is negative. In other words, it's decreasing when, let's see here, so what values make this decreasing? Well, ln of x would have to be bigger than 1, right? So this is going to be decreasing when ln of x, so when ln of x is, greater than 1. But let's put that in context of x, not just ln of x. So, i.e., when x is greater than e. Okay, so we have the slope is negative, so it's decreasing when ln of x is greater than 1, and that's going to occur when x is greater than e. So let's just put this right here. So f is decreasing when x is greater than e. So we can apply the integral test. Okay, and remember, one of the notes that I made about the integral test is that it doesn't have to be decreasing the whole time. Okay, it doesn't have to be decreasing starting at 1, as long as it's decreasing in the long run. Right? And so technically we're starting at e instead of at 1 for the decreasing portion of it, but in the long run it is decreasing. So that gives us what we need. Okay, so we can apply the integral test. So let's integrate. So we have the improper integral from 1 to infinity of ln of x over x dx. So this is the limit as t approaches infinity of the integral from 1 to t of ln of x over x dx. Right, you would have to do a u substitution on this one, or you can just kind of work through it, right, reason through it. Right? So you use u as ln of x, then du is 1 over x dx. So you get the integral of u du. Take the antiderivative, that's u squared over 2, which is just ln of x squared over 2. Okay, so I'm just kind of blowing through those steps, but you can go back and practice with your u subs as well. That would be just great. So we get ln of x squared over 2 evaluated from 1 to t. So that gives us limit as t approaches infinity of ln of t squared over 2 minus ln of 1 squared over 2, but ln of 1 is just 0, so that whole second term is 0, so I'm not even going to write it. But this, so as t goes to infinity, ln of t also goes towards infinity. It gets infinitely large, and then it's being squared and divided by 2. So this is going to head towards infinity, okay, as t grows infinitely large. All right, so the integral test tells us that if the integral is divergent, so is the series. So, since the integral is divergent, the series ln of n, ln of n over n is divergent by the integral test. Okay, so a little bit of extra work on this one because we did need to verify that it satisfied those conditions first, right? Especially the decreasing condition. We found out that it did, right? In the long run, it did. So we got the improper integral, it diverged, so the series must also diverge as well. Okay, so next up, so we're going to take a pause here for this section because we do have a couple more pages to go. Give you guys a little bit of a break in between. When we come back in just a minute, we're going to work on estimating the sum of a series. Okay, so we're going to look at using these tests to not only determine convergence and divergence, but